Hello everyone. Today we are solving a toy problem with dynamic programming. The problem at hand is a real-world problem, and I hope it will help you comprehend how dynamic programming works, and also it will help you to use this method on real-world problems. Okay, the problem is there is an electric power company, and they are planning to a large investment in power plants over the next few years. So in total, they will build 8 power plants in the next 6 years. In this problem, we know the demand of this region per year, and also the cost of these power plants changing over years. So initially the plant cost increases until 2002 because of some electricity crisis. Then, due to the advancement in the technology, the price goes lower. So the company should decide how many power plant they should build in the next 6 years. So it's an optimization problem, but there are more constraints. So according to homologations or regulations, they can build up to 3 plants per year. Another rule, if they build any plant, then they have to pay additional $1.5 million just for once. So if they build 3 power plants, they will still pay 1.5 million. Okay, so before I start solving the problem, I want to show you the notation that I'm using, and also I will talk about how we construct these dynamic programming problems. So let's use this paper, draft paper. So in dynamic programming, the purpose is to define a state. This can be a cost, this can be the route length if you are optimizing the route. So we will decide on something, either we buy or either we choose different right or left lane, different traffic lights, whatever. And we will observe an output. This will be the cost of this operation. So based on the state and the decision. So this is called stage. Okay, we will solve this problem in backward recursion. So we will start from the last one till the first state. So from n, we will go to n minus 1. This is another stage, another decision, n minus 1. And the outcome, the return becomes f subscripted n minus 1. So it continues like this. Okay, dynamic programming strongly assumes cost is additive. So if we define a cost, we can sum all of them up from the first time step till the last one if it is time dependent, or if it is like a route planning, then you will sum up all the cost of each route segment. We will solve the problem in backward chaining. So according to this notation, the problem becomes maximization of this return dn sn. Okay, I write it recursively as minus 1. Okay, so in our problem, we are trying to minimize the total investment, so it will be the minimization of the cost. So roughly this is what will we do. Okay, we have 6 year, all the demands over 6 years, and then the cost per plant. So before we start, I think it's easier to comprehend on a network graph. But of course, while solving it with programming, you don't need to do this. Okay, in x-axis, let's put the time. So year to go. So in the beginning, there is 6 years to go until 0. Let's put them like this: 5, 4, 3, 2, 1. And in total, we need 8 power plants. So you can skip this part if you don't need to write the problem. Okay, so at the end of this process, all of these years, we have one criteria, we need 8 power plants. Let's put one node here. So previous year, we can either have 8, so this is the minimum requirement, or we can invest earlier and we can already have 8. Okay, it will confuse. Let's put some axes here. I hope it's clear in the video. Okay. I will use another pen. So, okay, the black one. Then we need at least 6 in 2003. I'm still writing down the problem. So 2 years earlier, the end of this whole process, we need at least 6. So this is the demand of the city. So three years earlier, we need at least 4. So we should have at least 4. So this is why I'm not putting any notes below. This is the demand. We will also use maximum 3 plants per year constraint. Okay. Let's continue. We will need at least 2. Actually, we can invest, I think, up to 8. We will see. Then we can cancel the ones which are not satisfying the condition. So in the beginning we have 0. The first year we need at least 1, but we can have more. Okay, we are not putting 1 here, 1 node here, because we can put maximum 3 plants. So from 0 to 3 in 1 year. Okay, the next year we can have more, from 3 to 8. Okay, let's connect all the nodes, all the possible nodes, so we can plant 1, or we don't plant any, we just sustain them. Okay, from 4 to 8, no, it can't happen. So 4 to 7, yes. 4 to 6, yes. Okay, maybe I can speed up this part. I think you understood the problem here. So we can plant up to 3. Okay, here, I think they are done. Okay, so in dynamic programming, we use dynamic programming tables. So at each time step, we will create a cost table and we will choose the minimum of it. So if we sum all the minimums, it will lead us to the global minimum cost for this problem. So let's say table 1. Okay. So here I will call how many plants we build k number with m of plants to build. Okay, then x is our state. It was s, let's use s, is our state. We start solving from the back. So I skip the first one, which we have 8 of the plants, so there is nothing to build, there is no cost. So we come here, so we will start solving from here. This is table 1. Okay, so our state can be 8 or 7, so we can either build 0 or 1. So if we build 1, we just go 1 box up. If we don't build, we just continue. So the cost of not building anything is 0. Okay, let's use another constraint. So maximum we should have 8 plants. So let's say the s plus k should be smaller, equal than 8. Okay, so if you don't plant any, if you are at 7, it's not possible, because we should know s plus k should also be greater than 8 for this table. So there's only one option then, 8 plus s plus state plus number of plants we put is 8. Okay, so this is impossible. Alright, so the cost of putting one plant in 2005, so we start from back, so we will go this way in time as we do in dynamic programming. Okay, so the cost is 1 plant 1 times 5,200, of course, times so much money, so $5.2 million, plus this additional cost, which is 1.5 million, but I won't use these 3 zeros, so it is $6,700. Perfect. So if you write our returns 6, 8, so this is time 6, we start from the bottom, times 6, and if you look at this case, so if we had 8 already from previous state, the cost is 0. So at time 6, if we had 7 already, to reach the goal we need to invest $6,700. Okay, let's see, this is page 1. Okay, I have to, can you pause the video if you need to write anything from there? I will close this part. Okay, let's continue with table 2. So in table 1, we saw we had 2 cases. We can build the plant, or we can just continue with 8, so we can plant it earlier. Okay, so table 2, so the time step is 5. So let's see, the demand is 6 this time. The demand is 6. So the state plus the number of plant we built sums up to at least 6 and smaller than 8. State and number of plants. So we look at here, table 2. So the state could be 6, 7, and 8 from previous step. So we can build 0, 1, or 2. Actually, we can build up to 3, but here if you put 3, none of these cases will satisfy the condition. So it will go at least 9. Okay, so the cost of not building anything is 0. And if you build 1 over 8, we will exit this value. Okay, so if you already had 7, and if you build 0, the next stage, so basically the previous one in the calculation, we solve it in backward, should complete the whole purchase. So this will be f times step 6 and state 7. So I will put the value here. Oh, sorry, you don't see that. I put the value here. Or we can build 1 and we finish the whole process. So to build 1, let's check the cost here. The cost is 5,500 plus additional cost that we always have, $1.5 million. So if you sum them up, it is $70,000 times some other numbers. If you build 2, it will exit 8, so it's not a case for us. Okay, the next stage, so in table 1, we needed at least 7. So if you don't build any over 8 over 6, then it doesn't satisfy the condition. So we can't purchase in the next stage because of the demand given by the problem. Okay, so if we had 6, if we built 1, then the cost will be completing the purchase plus building 1 here. So 6,700 plus 5,500 plus 1,500. So 13,700. Or we can directly build 2, which is 15,500 times 2 plus the one-time cost, 12,500. Okay, so we will minimize each. Let's write the return the time 5. If we end with 8, so state 8, we spend 0. So this is the decision is actually not building anything. Let's also put the decision here. So the K 0 time 8. If we end at 7, we will compare now 6,700 and 7,000, and we will choose the smaller one. So if you minimize each expense, then we can minimize the overall, because as we said, dynamic programming assumes additive cost. So here it is 6,700, and if we end with 6, we will compare these two. We will choose the small one. So this was the case. We chose not to build anything. Again, the decision is 0, and here we choose the minimum one, and which corresponds to building 2 power plants. Okay, table 3, time step 4. So the demand, let's check the table again. The demand is 4 this time. quickly. Let's write the constraints s plus k smaller than 8. We can build 0, 1, 2, 3. Let's look at the graph if it is correct. So if he had 5, yeah, we can, so this will be table 3 here. So it can take all the states. So 8, 7, 6, 5 down to 4. So building this, constructing this network is important to comprehend which states are possible for the next time step. Okay, again, if he had 8, 0, and others are not possible. So here, if we end up with 7, so we will need the previous table, so the next time step. So if we end up with 7, we will need additional this much money to complete the invest in this plant. Okay, so it is 6,700. Okay, if you build one, so what is the cost at this time step? It is 5,700. So 5,700 plus one-time fee, 7,200. And if you put new 2 plants, then it will exceed this number 8. So we don't do that. Okay, so if we already had 6 from previous time step, if we build 0, so the next timetable should be able to complete it, which is a case, it's here. So we will put that number, and we don't spend money at time 4 if we choose this. Okay, so if you build to 1, then at the end we will have 7, so we will need to spend this much money, plus we will pay for this new this new plant. Okay, so we know we have 1,567 from the previous one. What is the cost? It is 5,700. So it becomes 72, 13, 900. Okay, if we plan 2, it's easier. Directly 11 for 100, so 2 times plus 1 time fee, which is I guess 12,900. Okay, so if you had 5, if we subtract 0 new plants, then there is no case satisfying in next time step. So they are just not possible. I solve the problem. So if we end up with 6, is this case, plus 1,500 plus cost of building a new one. So in total, 14, 19, 700. Okay, so if we end up at this, and then we build 2, and then 1 time fee. Okay, it's getting more and more complicated. And yeah, we can also build 3 of them, which is just simple calculation. There is no case. Let's find this. We can end up with, and we can build 2 more. plus 1 time fee. Okay, this is 25,400, or we can end up with 5,7K plus building 3. So in total, this is 25,300. All right, let's minimize. And decide which decision is the best. So this is the meaning of this horizontal line. So at time step 4, if you end up at 8, if in time step 4, if you end up at 7, 4, 6, 4, 5, and yeah, and also here F4, 4. Okay, so in this line the smallest number is 0, which is the only number. Then here it is again 6,700, and the decision is 0, and also here 0. Okay, let's continue here. The minimum number is 12,500, and the decision is again 0. Smallest one times step 5 is this one. Decision is building 3, new power plants. Okay, this one. No, okay, this is here, this is there. So this is the smallest one, 25,300, building 3. Okay, this time I will try to be neater. Table 4 times step 3. Decision, so not the decision, the demand is 2, s plus k is greater than 2, s plus k is smaller than 8. Okay, I will start putting the numbers directly. Okay, let's look at the table 4. We moved one step. This is table 4. So it can take values 6, 5, 4, 3, 2. So these are the possible values for our state: 6, 5, 4, 3, 2. Okay. Okay, let's also see the table here. Okay, we can't see both of them. We will switch. We can build 0, 1, 2, 3. Okay, I will put the numbers. So again, I look at this. So if I end up with 6, then I will need to complete it the next time step. So basically these numbers are just these numbers. 25, 300, and these are not possible from there. So if you put one new plant, it is 14,000. And if you put 2, it is 13,100. Okay, I already calculated these values. $25,600. If you put 3 plants, it's $25,600. Okay, 32,600. 31,700, 38,400, 31,400, 37,500. We will minimize. The cost. Okay, 3 and status 6, 3 with 5, 3 with 4, 3 with 3, 3 and 2. So let's look at the minimum numbers. So if you don't plan anything, that's the best for this time step. 0, here it is 18,600, and again we don't build anything. Again, if you don't build anything, it is the best. Here if you build to 3, it is the best with the minimum cost 37,500, and this is when we build 3 new states. Okay, I will find clean paper, almost clean paper. Let's fill table 5 and then 6. Okay, I will speed up here. So let's see the states. So table 5 is here, 3, 2, 1. So we can build 0, 1, 2, 3. Okay, from previous one, 37,500. I'm reading the values if you can't read my handwriting. 32,400, 38,500. To be honest, I can't even read my handwriting. 31,300, 38,000, 44,100, 43,600. Okay, let's write the returns. Can minimize these. So here 800, 36,900 and 43,600 also. Which decisions there if you build 3 for all of them. So finally, I hope you can read everything. Okay, we look at the network. There is only one, which will be the final case for us. So we can build 0, 1, 2, 3 for the first case. Okay. Basically, if you don't build anything, there is no cost and there is no problem. You have to start with at least one. Okay, so this is 43,600 plus fee of building 1, 5,400 plus 1,500. In total it is 50,400. So just the same way I fill the table. Okay, 48,500. So time step 2 time step 1. So 1, 0, okay, it is the minimum of this, so it's 48,500 and the decision is 3. So we reach the bare ground. So this is the first time step. So we completed the problem. So now we can look at the decisions we took. Okay, I think it should be 3. Okay, so we start with decision 3. Now we will go in forward flow. We completed the backward recursion. Okay, so according to the first step, we chose 3. The next one. So now we have 3. So from 3, we chose another 3. So we said 3. Now we have 3 power plants already. And we look at the problem with 3 power plants. So we choose again 3. Okay, let's look at other timetables. No, DP tables. Now we have 6. 3 plus 3, we have 6. So the next one is 0. Again, we have 0. Again, 6, because we didn't put any. So we decided 0 again. Still, we have 6 plants. So this time the decision is 2. So basically 3, 3, 2, we reached 8. But we can still see it will be 0. So we already have 8. So it is 0. So this is how many power plants we build every year. So in 2000, 2001, 2002 till 2005. So this is the most optimal purchase mechanism strategy for this company. Okay, in the end of the video, so right now, as I promised, I will show you the solution of the problem in Matlab, and also you can find the code in the description below. Okay, see you in the